Mobile communication system has gone through several evolution stages in the last few decades after the introduction of the first generation mobile networks in the 1980s. Due to huge demand for more connections worldwide, mobile communication standards have advanced very rapidly to support more number of users. Let's take a look on the evolution stages of wireless technologies. 1G, the first generation of wireless telecommunications. 1G began in the late 1970s and continued throughout 1980s. 1G introduced analog voice for the first time. The technologies used were AMPS, NMTS, TAX and ETAX. And the technique used was FDMA, Frequency Division Multiple Access. The maximum speed achieved was 2.4 Kbps. But 1G had many limitations. Poor voice quality, large phone size, poor battery life, and limited number of users, and the call rates were also too high. Roaming was also not possible between similar systems. However, 1G was phenomenal, but it was not enough. Then comes the second generation, the 2G. 2G was a revolution in the telecommunication sector. 2G introduced digital voice and SMS. With digitalization, the quality of voice was greatly improved. 2G was first introduced in 1991 in Finland with the technology standard GSM, Global System of Mobile Communications. Then with an intermediate generation 2.5G, GPRS was introduced, General Packet Radio Service, which implemented packet switching for the first time, which improved the speed greatly, up to 53.6 Kbps uplink and 26.8 Kbps downlink. With this speed, GPRS introduced MMS to send media like pictures. GPRS also supported IP to connect to the internet. Then with 2.75G, the EDGE technology was introduced, Enhanced Data GSM Evolution, to improve data rate of GSM networks. EDGE, the symbol is E. EDGE was capable to support up to 473.6 Kbps. All the second generation used the multiplexing technologies CDMA, Code Division Multiple Access, and TDMA, Time Division Multiple Access, as opposed to FDMA, Frequency Division Multiple Access, which was used in 1G. Then comes the third generation, 3G, which was first introduced in 1998 in Japan by NTT. High speed of voice, internet, and data access became possible with the increased bandwidth. 3G used the technology standards WCDMA, UMTS, HSPA, and HSPA+, and the multiplexing technique used was CDMA. Maximum speed achieved was 40 Mbps with HSPA+. You can notice that your phone connects to H+ when 4G isn't available. Multimedia, mobile apps, video calling, media streaming, mobile internet all saw their inception in the early 3G era. The term mobile broadband was first introduced. International roaming was also possible. Also, 3G used a hybrid model, circuit switch for voice and packet switch for data. This was revolutionary because users paid only for the data they spent rather than for the time they spent online. However, the main limitation of the 3G is low speed, and also we cannot use the voice and data at the same time. And also it required costly mobile devices and the power consumption was too high. However, 3G showed us the unending potential of data, yet did not fulfill its full potential, which brings us to the fourth generation, 4G. 4G was a complete redesign and simplification of 3G network architecture. It is much faster and better than 3G. 4G came with two standards, LTE and WiMAX. However, LTE was the winning technology. The key technologies that have made 4G a revolution are MIMO, multiple input, multiple output, and OFDM, orthogonal frequency division multiplexing. These technologies helped 4G introduce VoLTE, Voice over LTE, which allowed users to access data and make calls at the same time. Data speed, quality, and security were greatly improved as well. The maximum speed of a 4G network when the device is moving is 100 Mbps. High speed and low latency of 4G supported many use cases. IP telephony, VoIP, 3D television, video conferencing, mobile web, HD mobile TV, gaming, and cloud computing. 4G introduced us to a faster world and greater data capacity. People thought they had everything for mobile telecommunications. But soon, new technological ideas such as IoT, driverless cars, massive sensors, and even remote surgeries emerged. The need for new wireless technology showed up. And 5G is thought to be the solution for all these dimension targets. 5G, the fifth generation. With 5G, virtually everything and everyone is connected. The world will go truly wireless. 5G uses new radio access technology called the New Radio (NR), which was developed by 3GPP. 5G uses new technology standards EMBB, MMTC, and URLLC. Like 4G, 5G also uses OFDM, orthogonal frequency division multiplexing. The big changes in comparison with previous technologies are beamforming and massive MIMO, where large set of antenna are used. 5G is not an upgrade to 4G, but is in a league of its own. 5G is designed to deliver ultra-fast, ultra-low latency, more reliability, massive network capacity, and high secure mobile networks. Theoretically, 5G speeds can reach up to 10 Gbps, which is about 100 times that of a 4G peak speed. 5G provides us the ability to connect thousands of devices at once, giving the user a true sense of real-time experience. Virtually everything and everyone, machines, objects, devices are connected. Let's look at the various use cases and the applications of 5G. Nowadays, telecommunication is used for different areas for different needs. For some use cases, the amount of data transfer is critical. For some others, latency is the key issue. And for some other use cases, massive number of devices need to be connected online at once. And for some other use cases, fewer devices but high data rate. So 5G has divided these use cases into three categories: EMBB, MMTC, and URLLC. For the first time, a wireless generation introduced different standards for different use cases. Let's look at these categories of use cases. First, EMBB, Enhanced Mobile Broadband. EMBB deals with applications where the amount of data transfer is high. EMBB is a direct evolution of 4G LTE networks and aims to provide higher bandwidth, high speed, and better latency. Data speeds could eventually be as much as 20 Gbps. With such high speeds, EMBB will enable new applications such as 4K, 8K video streaming, video conferencing, 3D gaming, work and play in the cloud, and truly immersive VR and AR. Imagine watching a VR streaming of a football game. EMBB will also enable smart homes and buildings. Second, MMTC, Massive Machine Type Communications. MMTC deals with applications where massive number of devices need to be connected online. MMTC supports extremely high connection density of online devices of up to 1 million devices per square kilometer. This is over 10 times higher than 4G LTE network capability. With this ability, MMTC focuses on IoT applications such as smart cities. Within the smart cities, we could place thousands of traffic cameras, radar traffic counters, and air quality sensors, and by analyzing the data from these devices, we could reduce traffic congestion, deploy emergency services, and also improve the air quality for the residents within the smart city. Smart cities can also use high number of sensors to monitor utilities such as water, gas, electricity, and also they can do waste management very efficiently by reducing the operating costs. MMTC has a wide range of applications: smart cities, smart homes and smart buildings, intelligent agriculture systems, patient monitoring systems, and traffic management systems, etc. Third, URLLC, Ultra Reliable Low Latency Communications. URLLC deals with mission critical applications. that require the real-time control of the devices with extremely low latency of approximately 1 millisecond for data transmission and also high network reliability, more than 99.9999%. A great example of URLLC type application would be autonomous or self-driving cars or driverless cars. Autonomous driving has a lot of benefits, from time saving to improving safety by eliminating the user error. However, it needs all the vehicles and systems need to be connected. Vehicle to vehicle communications and to roadside systems, traffic light systems, emergency services, road maintenance programs, everything needs to be connected. Data would need to be shared in real time with minimal latency, as safety requirements also demand ultra high reliable connections. URLLC provides these kinds of services where latency and the reliability play a key role. There are many other applications of URLLC: vehicle-to-vehicle communications, industrial robots, remote robotic surgeries where microseconds matter, augmented reality and virtual reality or AR and VR, and much more. So those are the use cases and applications of 5G. 5G will make the world truly wireless. Now let's take a look at the key changes in 5G compared to 4G that make 5G achieve ultra high speeds, ultra high reliability, low latency and massive capacity. If we compare 4G and 5G, we can see that 4G used to support maximum of 20 MHz bandwidth, while 5G can support up to 100 MHz for FR1 and 400 MHz for FR2. This will significantly increase the data speeds and the number of users supported. Coming to the frequency bands, 4G can only support low and mid-range frequencies, that is 600 MHz to 5.9 GHz, while 5G can support higher frequency bands like in FR2 where range is about 24 GHz to 54 GHz. By using higher frequency ranges, 5G can take full advantage of beamforming technology to get higher speeds. Other changes are in MIMO technology, where 4G can use up to 8 layers, but 5G can support up to 64 layers. Latency is also greatly reduced in 5G. Mostly in every generation, from 1G to 5G, key changes occur in physical layer or layer 1 and MAC layer or layer 2. MAC layer controls and schedules the users over air interface, and physical layer uses complex algorithms to transmit and receive data over air interface. Now let us look at the key changes in the physical layer and MAC layers of 5G compared to 4G. Flexible frame structure. In 4G, only one subcarrier spacing, that is 15 kHz, was supported. But 5G NR introduces something more interesting. 5G brings in the concept of flexible subcarrier spacing. In addition to 15 kHz, 4 additional subcarrier spacing, that is 30 kHz, 60, 120 and 240 kHz are introduced. This reduces latency. Second, smaller scheduling period or mini slot. In 5G MAC, a new feature called mini slot is introduced, which reduces the scheduling time, that is scheduling in symbol rather than in slots. And with combination of enhanced HARC feedback feature, which is a release 16 feature, we can receive HARC ACK in the same slot. These changes also tend to reduce latency. For reliable communication, a new feature called Optimized Low Rate MCS QCI is introduced in 5G. Higher aggregation levels are also supported in 5G. In 4G, the maximum aggregation level was only 8, but in 5G, up to 16 level aggregation is supported in PDCCH. Retransmission of mini slot is also supported from release 16 in 5G. In 5G, handling of PDUs and SDUs have also changed. In case of 4G, 4G RLC used to prepare the RLC PDU only after MAC sends the grant for the downlink. But in case of 5G, as concatenation is removed, 5G RLC prepares the PDU before the MAC grant and sends the PDU to MAC by just modifying the RLC header. This is just an overview of the key changes in 5G compared to 4G. But as we go deep into these layers, physical and MAC layers, we can see more such changes in 5G. The 5G is here to transform wireless communication systems. Among all the use cases we have discussed earlier in this lesson, currently the mobile broadband is in high demand. Consumers are using more data-hungry applications like 4K live streaming and online gaming. So EMBB was the first 5G service to be rolled out for real-world applications. Many operators globally sense the opportunity that this presents and are engaged in acquiring the spectrum, network planning, and deploying the 5G services commercially at scale. Now let's take a look at the overview of various options available for deploying the 5G services. Option 1. Standalone RSA. Option 1 represents the current deployment model of 4G LTE, which runs on Evolved Packet Core or EPC. In other words, we can say this is the legacy deployment of LTE radio connected to the EPC that has no relation with 5G. Option 1 is not 5G at all. It is there more as a reference or starting point. Option 2. Standalone 5G or 5G SA. It is a pure deployment of 5G services, where the services are provided through an end-to-end 5G network. It uses the new 5G radio access technology, NR, new radio, which runs on 5G core, 5GC. This option is most suitable for a new entrant into the communication service provider business, where the operator does not have any legacy LTE system deployed, or even for an existing operator if it wants to offer 5G only service without 4G interworking. This is a good option to consider for full-fledged 5G deployment. This type of deployment also allows the operator to implement all types of use cases like MMTC, EMBB, and URLLC, provided it has the necessary spectrum allocated for each type of service. But deploying a full-fledged 5G infrastructure is expensive. That involves in high investment. To increase the coverage, the service providers must deploy large number of 5G towers close together. And with existing technologies, this results in high deployment costs and complexity. Also, higher level of training required. Without proper revenue models, the operator may run into huge losses, which brings us to the third wonderful intermediate option. Option 3. Non-standalone 5G or 5G NSA. In the non-standalone model, the operator can take full advantage of existing investments and LTE architecture. In this case, the 5G radio access network 5G NR has to be newly implemented. In this model, the 5G NR is overlaid on an existing 4G LTE network core, and the operations in the core network are supported by the existing Evolved Packet Core EPC from LTE. While operating in NSA mode, a device will first connect to the 4G LTE network, and if 5G is available, the device will be able to use it for additional bandwidth. In this model, the operator provides services by a mix of older and new technologies, that is, a mix of 4G LTE and 5G. 5G is here to transform the wireless telecommunications. 5G will make the world truly wireless. Many operators are beginning to roll out 5G services, but it is quite unlikely that the 4G will go away immediately. Many operators are rather choosing the 5G NSA mode to deploy 5G services, and eventually they will deploy the full-fledged 5G infrastructure with 5G standalone mode. This will bring many use cases such as EMBB, MMTC, and URLLC. Among the primary advantages of 5G services are low latency and massive number of IoT devices. Sooner or later, the world will run on 5G. Welcome to the fifth generation of wireless telecommunications, 5G.